I've got a digital multimeter that has a temperature measurement capability. The sensor is at the end of these leads. Right now, it's measuring room temperature, which is about 23 degrees Celsius. I want to measure the temperature, so I'll tape the sensor to the bottom of the pan. Now I'll turn on the stove burner, which adds heat and causes the pan to warm up. This is a lightweight stainless steel pan which warms up pretty quickly. Even so, I'm going to cut out some of the time while it's getting to the temperature I want, which is about 100 degrees C. The pan's at the temperature I want now, so I'll add a cup of water to the pan. The pan temperature, as you'd guess, drops when the water cools. The lowest temperature it reaches is about 47.3 degrees C before it starts to warm up again. Now let's do the same thing with a heavy cast iron pan. Since this pan has a higher heat capacity, the temperature increases more slowly. It's pretty boring to watch a frying pan heat up, so let's cut that part again. Now the pan's temperature has gotten to the 100 degrees Celsius that I wanted, so I'll add a cup of water. The water again cools off the pan, but this time the minimum temperature the pan reaches is about 90 degrees. Since the pan stores more energy, there's more heat left over after the water absorbs part of that energy. If I'm actually cooking something, the cooking process doesn't suspend temporarily while the pan reheats after adding the food. This can sear the food early in the cooking process, which can result in tastier results. Now let's take a look at the math that describes our measured results and our intuition. Here's my frying pan. My pan has some heat capacity, which is the mass times the coefficient of specific heat, and some temperature, which I'm going to call T sub B. I'm going to be adding some heat to the frying pan from my stove burner. That I'm going to call Qn. The pan will also radiate heat out to the environment. So there will be heat leaving the pan, and that I will call Q out. Now before I throw some equations around, let's make a few observations about this. This one's really important. We've assumed that the pan has a single temperature TB. So there are no temperature variations across the pan. Every point in that pan has the same temperature. That implies that this is a lumped parameters model. So all the energy storage is in a lump in the pan, and there is no variation in energy across the pan itself. There's also an ambient temperature. I'm going to call that T0. The heat leaving the pan, Q out, up here, will be a function of T0. It's the temperature difference between TB, the pan temperature, and the ambient temperature, T out, and also a function of the temperature of anything we put in the pan to cook. The equations governing this, and this comes from a conservation of energy, is the change in the pan's stored heat, which is the heat capacity, mc sub p, times the rate of change of the temperature of the pan minus the ambient temperature with respect to time. So this term here is a change in the pan's stored heat. And the change in the pan's heat will show up as a temperature change in T sub B and T0. This change in the heat stored in the pan is the difference between the heat being put into the pan and the heat that the pan is radiating out. So this term here is just a difference between the heat added and the heat lost. So if I add heat to the pan that I'm not radiating out to the environment, the pan temperature is going to go up. I don't want to get into much detail about deriving this equation or solving it, but I do want to mention a couple of things that this equation tells you. If the heat capacity, mc sub p, gets higher, that means the pan can store more energy at a given temperature. Another thing about this equation, the term mc sub p is what is mathematically called a time constant. Roughly speaking, the time constant is how fast the system can respond to some change in input. So this is going to tell us how fast the temperature responds to some heat input Qn. So the higher MC sub P is, the longer the time constant is, and the longer it'll take for the pan to respond. So all of this math tells us that if I increase the mass, M, I'll store more energy as heat for a given temperature. Also, the temperature will respond more slowly, which is exactly what we'd expect from our experience. So now we've got some math that tells us that a heavy pan cools less than a light one if we add food to it. It's comforting, but that seems pretty useless since we already knew that's what would happen. However, engineers generally have to solve problems that require numerical answers. For example, maybe we want to know how long it's going to take to heat something up. Or maybe we need to design something so that it heats up within a given time. No amount of intuition is going to help you give a satisfactory answer to those questions. We need to write the equations and make a number. As a final point, remember that our equation assumed that the pan properties were lumped. We assumed that the pan had a uniform temperature, T sub B. However, if you were watching the demonstration closely, that was pretty obviously not true. The water around the edge of the pan was boiling, and the water at the center of the pan wasn't. This implies that the outside edge of the pan is hotter than the center of the pan. So if the engineering question we have to answer is something like, what's the highest temperature that any point in the pan will experience, this lump parameters model won't give us a useful answer.